Today we are going to discuss sliver feed arrangement, that is the feed unit of the machine. So, sliver feed unit, what are the objectives of sliver feeding? Number one is the unit should be capable to feed the sliver at a constant rate, at a uniform rate the sliver should be fed. Number two is fibers finally are to be separated from each other, that is fibers will be arriving in the form of a sliver and we have to separate the fibers from the sliver and make them move. And the third is we have to remove trash particles when we are processing cotton fibers. Because we all know that the sliver still contains lot of trash particles. Though large amount of cleaning is done in the blow room and in the carding machine, but still some amount of trash will be left, and these trash particle is a nuisance. We will see that is a nuisance for the performance of the rotor spinning. They create a lot of problem for us. So, removal of trash is also an important aspect of sliver feed unit. Trash removal is not required if we process 100% polyester or 100% viscose rayon or such man-made fibers where trash does not exist. A unit is shown here: feed roller, feed plate. This is the zone where trash particles are escaping. Then we have the opening roller. On this side, a real opening roller image is shown. Then this is the transport channel through which the separated fibers will move and reach the rotor box. The rotor is here. So, this is a cross-sectional view of the sliver feed unit. If you look at the specification of the opening roller, this roller will be having a diameter between 60 to 80 mm, which may it differs depending upon the manufacturer. Then the width of the clothing that we see here, this width is around 18 millimeter. It runs at the speed of 5000 to 10,000 rpm. So, depending upon the kind of fibers I am processing, we can set the speed in this within this range. And the draft range between feed and opening rollers is 500 to 2000, again depends upon the type of material we are going to process, what is the sliver count, what is the yarn count, what type of fiber. Based on that we can decide how much draft is there between the feed and the opening rollers. We can find it out easily if we know the surface speed of opening roller and if we know the feed rate in terms of its linear speed. So, this is the opening sliver feed unit. It goes up to this point, transport channel, and opening roller action, if we try to understand, the feed unit will be able to feed the sliver at a constant rate, and for that what we have? We basically have a feed plate, which is this one. This is basically feed plate spring loaded, and then we have a feed roller which is here. So, feed roller feed plate combination will be feeding the sliver Sliver is coming from a can. So, sliver is lifted because of the pull from the feed roller side, and the feed roller is giving motion, and the roller rotates at a constant speed. The speed can be set separately. We can set the speed whatever speed we want, and at that speed it will continuously run and pull the sliver from the can. Now, once the sliver is fed and it comes into contact with the opening roller teeth, the opening roller is full of needles or saw tooth. Its surface is full with saw tooth. The action between these two, opening roller and the feed roller, is similar to what happens in carding machine, in the Likkernin region of the carding machines. There also we feed a lap or a mat of fibers, and this mat of fibers is opened by the Likkernin. Here a similar thing is being done. Instead of lap we are feeding a sliver, and instead of Likkernin we have a opening roller, but the action is same. Only the size of the feed roller and the size of the opening roller, they are much smaller in comparison to the size of Likkernin and the size of the feed roller that we see on the carding machine. Okay. There is a high contact pressure between feed roller and the feed plate. This much contact pressure is required, which is given by the spring. If the pressure is not there, the feed roller will not be able to pull the sliver. There is a chance of slippage. So, there has to be sufficient force. At the same time, if the force is there, the opening roller teeth will act on the fibers. The fibers are going to be pulled out by the teeth of the opening rollers. The teeth, the opening roller teeth are coming at a high speed, and it is then penetrating the front part of the sliver, which is here in front of the feed plate, penetrating this particular part of the sliver and pulling the fibers out. There is a huge difference in the speed. Teeth are running at a much faster rate than the rate at which the fibers are being fed. The feed roller should be rough. They have to be rough. Why? So that there is no chance of slippage. From here, from this nip, as the fiber end is coming over here and the opening roller tooth is trying to pull it out, there has to be some amount of resistance from the feed roller. Otherwise, a chunk of fibers will be simply plucked from the feed roller. To avoid such kind of plucking action, where a bunch of fiber is simply withdrawn from the nip, that is something which is not desirable. The friction has to be adequate enough between the feed roller, feed plate and on the fibers. So, in order to increase friction, the feed roller surface is either knurled or there could be flutes on it. Track ejection takes place where here. These black dots are actually trash particles. The trash trajectories are shown here by the arrow. So, as soon as the fibers are teased from the sliver, lot of trash particles also are trapped between the fibers. All these trash particles which are trapped will be combed out by the teeth of the opening roller. But because the trash particles, once they are combed out, they are free, they are thrown away by the centrifugal force. They attain the speed of the opening roller and they are thrown away. And these particles, there is an opening over here from here to there. This opening is large enough and a lot of trash particles are ejected as shown in the diagram. and we are in a position to clean the fibers at this stage. The purpose of the opening roller is not really to clean, but in the case of cotton we take the opportunity of the separation of fibers by the opening roller to clean it again. This may not be required in the case of man-made fibers. The trash ejections takes place in the combing zone, which is from here to there. This is the combing zone, and more is the kinetic energy of the trash particle, more of them will be expelled quickly. That means, higher the speed, the better it is. Trash ejection increases with increasing opening roller speed and opening roller tooth face angle. Like you have studied the Licarin teeth angles. So, here also the angle of the opening roller tooth is important, that is how much trash particles they will retain and how quickly they can be released from the teeth. It all depends upon the geometry of the Licarin tooth. The next slide gives you, while combing is going on, how the fiber fringe looks. Now, here the two diagrams are here. On the right hand side it is meant for cotton, on the left hand side is meant for polyester. If this is the nip line as shown it here, then in front of the nip line, as the fringe of fibers are being combed continuously by the teeth of the opening roller, the fringe will look like this in the combing zone as it is shown. For polyester it is something like a triangle, because in the case of polyester most of the fibers are of same length. In the case of cotton it is not really a triangle, because in the case of cotton we have fibers of different lengths. But this is the fringe which is continually getting combed or by the teeth of the opening roller. So, polyester viscose being same length, it will have a shape as shown it here. For comb, for the cotton the shape is little different, it is parabolic in nature. The density of the fiber fringe in the combed out zone depends upon three important parameters. One is the sliver linear density. How much is sliver linear density? It depends upon that. The other thing is the distance between the combing point to nip point. How much is the distance from the combing point to the nip point? That is also, that means the setting that we keep between the opening roller and the feed plate. And the other thing also what matters is the fiber length, that is what is the length of fiber, how much is the length of the individual fibers. These three are important, and you have to remember that in a dynamic state it is the fringe of this which is continually getting combed. Fibers are continually being fed and the fringe that exists in front of it looks like this as it is shown in this diagram. Fiber speed profile. Here again this same unit is shown here, and here we are showing you the speed profile of the fiber. Feed nip is here, from here to there the fiber speed is almost 0, almost nil, that means it is close to the speed of the your feed roller. Then from there up to a certain point you see there is no change in the speed of the feed roll, speed of the fiber, because fiber is still under the control of the feed roller. A fiber may have a length of suppose 40 mm. So, when the fiber appears at the nip of the feed roller, the leading end of the fiber appears. Now onwards it will be gradually fade. So, slowly and slowly it will move. So, it will move forward, and as long as it is held or under the positive grip we can say of the feed roller, it will continue to move at the speed of feed roller. There will be no change in its velocity, that is from here to there. From there, as soon as the trailing end of the fiber is released, the fiber is going to be anyway picked up immediately by the any tooth of the opening roller, and immediately its speed is going to increase, and this is how the speed will increase of the opening roller. Fibers will be accelerated and suddenly speed will increase. The velocity of the fiber has been shown to be 0.5 to 0.7 times the surface speed of the opening roller. DOR and NOR indicates the diameter and speed of the opening roller. OR stands for opening roller. So, fibers are on the picked up by the opening roller, and from as soon as they go from here to there, they cover this distance, they are about to be released now from the teeth of the opening roller, and they will enter a channel. We call it transport channel, transport tube, doffing tube, there are different names. So, fibers will be released from the teeth, they have to be released, and now they will start moving through this channel, and this channel is going where? It is reaching the rotor. The channel extends up to rotor. It starts on the opening roller housing, and it goes on the opening roller cover, and it goes up to the rotor, because we need to remove the separated fibers from the opening roller surface and want them to be within the rotor. So, because the fibers are held on the surface of the opening roller teeth, they are experiencing a very high centrifugal force. So, wherever there is a gap available, many of them will be thrown away, they should leave the teeth of the opening roller. So, how many of them will be able to leave, how many will be able to continue to move, all depends upon the tooth geometry. If the teeth is too acute in nature, in that case many fibers may not be able to be stripped, or they may not be released. So, there is the angle of inclination of the tooth of the opening roller is very important. And the second thing is that the suction, how the fibers will move from the opening roller to the rotor. This journey the fibers are going to make is through the air. So, there has to be a flow of air. This flow of air will be able to take the fibers along with them. That means, there has to be a suction system which will work through the rotor. The rotor is here, here is the rotor. So, rotor, within the rotor we have to create a negative pressure, and then only it will be able to draw air through the transport tube or feed tube, whatever we say it, and that air is actually entering here. You see, here is the air entry. So, this air is also trying to help in removing the fibers from the surface of the opening roller teeth. So, centrifugal force and the suction force, both of them are responsible for removing fibers from the teeth of the opening roller. And higher speed is better, higher speed of the opening roller is better, because centrifugal force will be also be more, fibers will go towards the tip of the opening roller, and therefore, they can be easily removed. If they remain buried between the teeth, if they remain towards the base of the teeth, then there will be more friction when you try to remove them, but the centrifugal force will cause them to move towards the tip, and hence the higher centrifugal force is beneficial for the removal of fibers from the teeth of the opening roller. So, many a times it has been found that in the case of actual processing, the opening roller gets completely filled with fibers and it gets jammed. So, jamming of opening roller is very common in the actual practice. So, one of the way to get rid of this jamming conditions of the opening roller is to increase the speed of the opening roller. That is one of the way to tackle the situations. That is not the only way, but that is one of the way. If we look at the opening roller technical details, opening rollers are available in two types. One is sawtooth type, another one is needle type. Sawtooth also has its own variety, OB20, B174, West. These are the type of opening roller tooth, and typical tooth geometry is also shown here. Oh, sorry. So, what is important is what is the pitch, what is the width, tooth density, pounds per centimeter square, what is the angle alpha and angle beta. So, typical values for cotton and man-made fibers are given, and the sawtooth is more, you can say it is more suitable for processing cotton and synthetic fibers as well. You can see a change in the value of alpha and beta, alpha especially when we try to process synthetic fibers, man-made fibers which are long. A needle type of tooth is also used when we want to process very delicate fibers, because needles puts less stress on the fibers. So, they do not damage the fibers, whereas sawtooth can damage the fibers, they can break the fibers also. They are very, very strong. So, in some cases where fibers are weak, and that means they are delicate, we can use needle type of teeth on the opening roller. Tooth arrangement, if we see, they are helically arranged. Why? Because it helps in fiber length between two lines of teeth being continuously subdivided into small strands resulting constant rearrangement of fibers in the fiber fringe. That is the reason why they are helically arranged. You should look at this teeth here, they are actually helically arranged, so that the fibers in the slivers can get subdivided easily. It helps individual tiny fiber groups to be pulled out and uniformly fed to the fiber feed tube. That is the reason that the tooths are helically arranged. Otherwise, they will form fiber channels. So, we have to break the formation of fiber channels. Fibers will wrap around they will occupy the space between the teeth. So, we have to break that, so that they do not occupy their space. So, otherwise, if the space is available between a series of tooth and they are all aligned together, then lot of fibers will go and settle there, and it will get filled up easily and it will lead to choking. So, if we want to avoid choking, therefore, we have to see that channel formation, how it can be avoided, and it is the way we actually arrange the teeth on the surface of the opening roller that really matters. That is how the tooth is helically arranged. How a fiber is treated by the opening roller tooth. Let fiber length be 40 mm. Surface paid to the feed roller is typically, let us say, 1.16 meters per minute. It could be 0.5, 1, 1.2, 2 meters per minute also, depends. Surface speed of the opening roller is 25 meters per second, and opening roller speed is, let us say, 8000 rpm. Opening roller diameter is 8 centimeter, and pitch of the tooth is 2.4 mm. If we do a calculation just to know how what a fiber is going to experience as they are fed by the feed roller. So, dwell time of fiber in the comb out zone. What is the dwell time? How much time they will spend? If 40 millimeter is the length of the fiber and 1.16 is the surface speed. So, it will be 1.6. So, 40 millimeter we divided it by 1000 to make it meter. So, that is the fiber length in meter, and the delivery fiber surface speed of the feed roller or delivery speed of the feed roller is 1.6 meter per minute. So, 1.6 by 60, and if we do this calculation, probably we will get a figure 1.5 second. So, this value, so only 1.5 second it spends. Number of opening roller rotations in 1.5 second. How many times the opening roller is going to rotate? We can also calculate, that is, if the speed of the opening roller is 8000 rpm. So, per second is 8000 by 60, and in 1.5 second it is going to rotate by how many times? 8000 by 16 to 1.5. What is this value? 200. So, that value will be 200. So, the opening roller's rotations is going to be 200. Next is circumference of opening roller is how much? pi d, pi into 8 centimeter is the diameter, it is became almost close to 25 centimeter. That is the diameter, that is circumference of the opening roller. So, number of teeth tips or tooth tips along the circumference is going to be how many? 25 into 10 by 2.4. That is 104. So, number of teeth acting on a fiber during this time, assuming that all the fibers are there, all the teeth are there on the, which are there on the surface of the opening roller, all of them are actually acting on them. So, in that case 200 into 104, that is 20,833. So, 25 centimeter converted into millimeter, no sorry, how much it is, 25 meters per second, yeah, it is okay. I think 25 centimeter converted into millimeter, 250 mm, and if the pitch is 2.4, the total number of teeth is going to be 104, and number of teeth acting on the fiber therefore will be 104 into 200, because it will, every revolution means 104 teeth will act on it. So, in 200 revolution, 200 in 104, so many teeth is going to, so many teeth are going to act on a fiber. So, roughly we can say that when a 40 mm fiber is being fed at the speed of 1.6 meters per minute, almost 21,000 teeth are working on it. So, opening intensity we can also find out, and we can say the intensity of the opening basically means the aggressiveness with which the opening roller teeth act on the fiber. So, factors that will affect the intensity, one is tooth geometry, that is point density and front face angle. How many tooth are there per unit area, and what is the angle of inclination of the teeth, front face of the teeth. Second thing is position parameters, while opening roller speed and sliver feed rate both are will have a influence on opening intensity. And the third thing is the setting, that is the clamping distance, that is the distance between the feed plate and the opening roller, or also known as combing roller. We can call it opening roller, or we can also call it combing roller. How much gap is existing between these two, that will also affect the opening intensity. Actually, this gap is very, very important. Too close a gap may cause lot of fibers to break, opening intensity will be too much. So, it is very important that how much gap we should maintain. The other parameters are tooth geometry, and generally once this setting is made, is not disturbed, we generally change the process parameters in order to increase or decrease the opening intensity. Excessive intensity leads to fiber damage, fiber melting, and difficulty in stripping from the roller surface. Everything is possible, that it can lead to damage of fibers, it can lead to melt spot in the case of thermoplastic fibers, mostly polyester fibers, this problem could be there, and difficulty in stripping from roller surface also could be sometimes there. As I said, there is a possibility of better stripping at a higher speed of the opening roller, that also is possible because of the higher centrifugal force, and at the same time there sometimes may be difficulty in stripping from the roller surface at a higher speed, because it may lead to fibers getting going towards the base of the tooth because of very high force that will be acting between the when the fibers are pulled by the teeth of the opening roller. So, it can be sometimes it can create difficulty also, especially with synthetic fibers, whereas in the case of cotton it may be beneficial from the point of view of stripping. So, stripping could be beneficial sometimes, sometimes it may not be as you go for higher speed of the opening roller. Trash removal is very important, and with the opening roller speed as we increase, the trash quantity within the rotor keeps on declining. So, if we have too trashy cotton that we have to process, we have to increase the opening roller speed, or we have to keep the speed at a higher level. Both the fibers and the trash particles are subjected to very high centrifugal force. Fibers can cling to the opening roller teeth because they are generally lighter and they have a long length. So, their contact area between the teeth and the fiber surface is always more in comparison to the trash particles, which are very dense, and therefore, they may not cling so well as the fibers clings to the teeth of the opening rollers. So, trash particles are easily released from the surface of the opening roller and they all fall down. So, we have a very big opening over here. The whole purpose of this opening is to allow these trash particles to get ejected and rush towards the chamber where there is a mild suction, that we keep on sucking the trash particles. What happens? Whatever we do, some fine trash particles still moves along with the fibers, and they will finally reach the rotor, that is, they will move towards the transport channel, and from there some trash particles will ultimately reach the rotor. In the rotor, these trash particles, some of them will get deposited, and there is no way to get rid of them. We can only reduce we can clean the fibers very well, but very fine dust particles cannot be removed by these means, and they go directly within the rotor, and they keep on accumulating within the rotor groove, and as a result they create disturbance to the spinning operation. They also can affect the quality of the yarn. Fiber transport part, if we try to understand, from the opening roller through this transport channel or fiber tube, these are the fibers as shown here, they are transported, and what is the the air is drawn over the opening roller, which passes through the tube to the rotor wall. This entire rotor chamber is actually connected to a suction unit, and we suck the air through the rotor chamber. This air helps in stripping the fibers from the surface of the opening roller and then direct them towards the transport channel. Fibers and fine dust particles arrive on the rotor wall, and then they slide into the rotor groove. Finally, they all reach the rotor groove, fibers will also reach the rotor wall, dust also will reach the rotor wall. From the wall they will go towards the rotor groove and they will accumulate there. The velocity of the air has to be more than the velocity of the opening roller. That means, the velocity at this point must be more than the velocity of the opening roller surface. Surface speed of the opening roller has to be less, then only fibers can be easily removed from the surface of the opening roller. These are very important conditions. Therefore, if we keep raising the speed of the opening roller, then the differential speed that we have between the air velocity and the opening roller, that will gradually reduce, and therefore, transfer of fibers or stripping of the opening roller surface will be difficult, unless we change the suction rate. The suction rate remains at a previous level, but we keep on raising the opening roller speed, hoping that this is going to improve the stripping. It may not, because the velocity of the air has remained at the previous level. In such situation, we have to increase the suction rate in order to increase the velocity of the air, which is we are drawing over the surface of the opening roller. The channel, we call it transport channel, we call it pivot feed tube, we may call it doping tube, whatever it is. This is tapered. The geometry is important, that it is a tapered channel, and this tapering has a beneficial effect, and that is that it makes the fiber straight. Why? Because velocity of air in and velocity of air at the output of the channel, this ratio is 5 to 6. So, the channel geometry is such that it is tapering gradually. At the exit end, the velocity is 5 times more than the velocity at the entry end. That way, the channel geometry is made. The fiber velocity is 20 to 60% less than the air velocity in general. So, velocity of fiber is always less than velocity of the air which is carrying the fibers. Because fibers actually traverse a very short distance. The tapered channel acts as a drop zone, which is 4 to 6. So, transport channel itself is acting as a drafting zone, because at the entry to the channel, whatever is the velocity of the air, at the exit of the channel, which is near the rotor groove, velocity is much more, and it is 5 to 6 times more. Therefore, there is a continuous increase in velocity. That means, there is acceleration that the fibers get, and fibers are separated out. So, whatever is the draft between feed roller and opening roller, that draft is now multiplied by 4 to 6 times before they arrive at the rotor. That becomes my total draft. So, if the draft, suppose at the feed point of the feed roller is 500, let us say, some figure we assume, and the draft, suppose there in the feed tube could be 4 to 6, let us say is 5. So, total draft will be 5 into 500, 2500. That is the draft which is going to act here. So, such a high draft will not be able to achieve by having normal roller drafting system. The roller drafting system, we are not capable to give such a very high level of draft to the order of 500, 600 like that is not possible. Now, we will take an example. Let us say calculate the average number of fibers flowing through the transport channel from the following data. The data what is given here? Sliver count, fiber fineness, opening roller diameter which is 65 mm, speed, sliver feed rate, these are the parameters which are given. We have to calculate average number of fibers flowing through the transport channel. How to go about it? Solution is given here. First, we will calculate how much is the draft between opening roller and feed roller. So, the draft calculation is simple, surface speed of the opening roller divided by surface speed of the feed roller. And if we do that, we will get a figure 1276. So, the draft between opening roller and feed roller is 1276. The next is, if that is the draft, now how many fibers are there in the sliver cross section? Sliver kilotex value is given, fiber fineness value is given. So, we convert both of them to tex and take the ratio. We get a figure 20,000. So, the sliver is having 20,000 fibers in the cross section. Therefore, average number of fibers in the flow will be how much? Because of the draft of 1276, we will get a figure 15. That means, on the opening roller surface itself, there will be 15 fibers in the cross section of the fiber flow. Since the draft practically cannot be too high even when opening roller fibers move in overlapping groups. Now, we can say that I told you earlier that we have to separate the fibers to almost single fibers, whereas actual case in practical situation we see there are 15 fibers in the cross section. Does it mean that it is not following the principle of open end spinning or not? Actually, it is not necessary that we have to have just one fibers in the cross section in the fiber flow. Even if we have groups of 3, 4, 5 fibers, it will still work. Therefore, here we get like 15 fibers, where on the surface of the your opening roller, because the draft between them is to the order of 1276. Now, rest of the draft is there in the transport channel. So, the 15 fibers which are being fed at the entry point of the transport channel, by the time they land in the rotor, there will not be 15. Cross section of in the cross section, you can say in that fiber flow or the fiber flux is going to be much less now. It will be reduced. Suppose if the draft in the channel, as we said earlier, can vary between 4 to 6. If we take a figure 3 or if we take a figure 5, then we will have 3 fibers in the cross section, and with this many fibers also the system is going to work. That is, the false twist will not be generated. Otherwise, the risk, as we have said earlier, as I have discussed earlier, that there is a chance that the twister will act as a false twister and would put twist on both the sides. If there is a continuity in the fiber supply and there is overlapping action or between the fibers, then this possibility is there. But if the ends are free to rotate, then this will not be there. So, here there is almost a break, because there is some more draft still available in the transport channel. Draft to the order of 3 to 5 is provided by the accelerating air in the transport channel, as I said, so which can vary between 3 to 5, somewhere you may find 4 to 6. So, it all depends upon the actual geometry of the transport channel. That will decide what is the tapering and taper ratio, we can say. From there one can calculate how much could be the draft. And here we are doing one more analysis of the fiber velocity within the transport channel. So, here a transport channel is shown, a simplistic diagram. The area at the entry is A in, area at the exit is A out, velocity of air is V in, velocity of the air out is V out, and BF is a typical fiber. This is the forward end, this is the back end, and this is the direction in which the fibers are moving. So, airflow rate is given, channel length is given, area stated, velocity at a distance x, suppose we want to calculate. As the fiber is travelling through this zone transport channel, what is the velocity at a point x on the fiber? Actually, in the actual case, the velocity at f and velocity of b will be different. F will move faster than b, but because there is the same fiber, the fiber will be under tension, and this is in a way helpful. This tension will actually straighten out the fiber. Because of this, fiber itself is accelerating, but because it has a length dimension and the two ends may have a they may differ in terms of 30 mm distance between them or 40 mm between them, it is we can assume that the front end will move faster than the back end, and if that happens, the fiber will be straightening out in the transport channel. So, this possibility exists in the transport channel that some fibers may get straightened out. Now, how much will be this velocity of the fiber or the air? Now, area of the tube at a distance x can be found out if we know the area here and the area at the output, and if we know what is the total length, which is L. So, what is L? Total channel length from here to there. This is what is not shown here in the diagram, this is what is L. So, we can find out what is the area added at a distance x, how much is this area, let us say here, which is at a distance x. This can be found out from this simple equation. Since volume flow rate will remain constant within the tube, hence the volume flow rate at a distance x is going to be whatever is the area multiplied by the velocity of air at that point, that is V x, into 10 to the power 3 into area will give you the volume of air which is transported. It should be equal to this value in millimeter cube per second. Q as you have seen in the previous case, is the volume flow rate, that we have, you have to see that the units are matching on both left and right hand side. Accordingly, you have to multiply by 10 to the power cube to make sure that the units are same on the both sides. They should match, they should tally. From there we can calculate what is Vx now. So, the Vx is given here. You see we can cancel 10 to the power cube both in numerator and denominator, and we will be left out with this formula, that is Vx is 16.6 q divided by A in minus A in minus A out into x by L meters per second. So, this is the velocity that we will get. If we know the air velocity, the fiber velocity will be little less, as we have seen it earlier. We will have some idea that the velocity of air from the entry to the exit, how it is changing and how much it changes, provided the geometry is given to us. That means, we must know the value of A in, the value of A out, that is what is the area at the entry side, what is the area at the exit side. If we know these two, and if its length L is also given, that means the geometry of the channel is known. Once the geometry of the channel is known, so geometry is decided by 3 parameters: area, the 2 places, and the length of the channel. We will be able to calculate what is the velocity of air at any point at a distance x. X will vary between 0 to capital L. So, that is the end of this session. Thank you. We will meet again in the next class.